everyone, welcome to the lecture 34 of the course Climate Change and Extreme Events. So, this is the last week of this course, week 12. So, in this particular lecture, we will primarily talk about review of the statistical and analytical methods. So, we have in the previous weeks, we have discussed about different types of statistical and analytical methods which can be used to, for example, can be used to determine the magnitude of the climatic extremes or their frequency of the climatic extremes, or let us say what is the historical behavior, or let us say you can also do some sort of stationarity and non-stationarity analysis. So, we will start with very basics. We will recap everything so that you can get an hold again on those statistical and analytical methods, and that will be helpful for your examining the climatic extremes of your study area, something like that. So, in this particular lecture we will recap what is the key statistical and analytical methods which we have already covered in this course. We will further understand the strengths and limitations of each method. Then we will further review use cases, when to apply different techniques, and prepare for project or application and for future research. In the next lecture after this, we will discuss about let us say if you are planning to conduct a study on climatic extremes on a particular region. So, how you can start with, right? So, that part we will discuss about the case study application of this course, how you whatever you have learned from this course, if you wanted to apply in a case study, how you can do that. So, that we will discuss in the next class, but in this class particularly we will primarily focus upon all the methods, statistical, analytical and machine learning, whatever methods we had discussed, we will cover all the techniques here. So, in the beginning of the course, we have started with different statistical measures. So, that is called descriptive and exploratory analysis. Suppose you have climatic extreme data at a particular location, it could be rainfall extreme, flood extreme, drought extreme, etc. So, you have some numbers that basically gives you an idea about how the drought behavior has been evolved in a particular region. Okay. Now, what do you do with the data? So, you have to calculate some sort of statistical properties, measures. Then you can tell us about whether the mean has been changed. Let us say you divide your data into two parts. Suppose you have data since from 1950 to 2020, okay, 70 years roughly data. Now, you can divide your data into 1950 to 1985 and then 1986 to 2020, like that. And then you try to calculate what is the statistical property of the first half of the data and what is the property of the second of the data. When you compare all these properties, you would be able to know that whether the statistical property of the data has been evolved also or changed through the time, or it is remained more or less same in a very 2%, 3%, 5% changes or something like that, which is insignificant. So, statistical measures is basically we have to calculate mean, which is basically represented the central tendency of the data value. Then there is another parameter which is also a central tendency of the data, which that can also show, that is median. Median is exactly, what is the difference between mean and median? Median is basically when you have the data exactly at 50%. You can divide your probability distribution function or curve or data set into equal part, 50% here, 50% in the right side. But when you are talking about mean, mean is always biased towards the extreme values. Let us say you have higher values, extremes more frequent in the data, then the mean will be slightly shifted towards the higher extreme side, or it will be little bit higher than median. If let us say we have more extremes in the negative direction or lower values, then in that case mean will be slightly shifted towards that extremes, and therefore, the median will be little bit higher than mean. So, like that. So, that is a simple difference. Variance is basically the spread of the data, how we can calculate what is the variability of the data, how much variability in the data set. So, you say mu plus minus sigma, sigma is basically called, or sigma square is called variance. So, variance or standard deviation basically tells about the nature of variability of your data set. So, in addition to these properties, there are several more. For example, you can also calculate skewness, skewed distribution. You can also calculate the kurtosis, that is the peakedness of the data, like that. So, that is called statistical measures of, that is called descriptive statistics of the data set. Suppose you have two parts of the data, you can calculate mean, median, standard deviation, or variance and kurtosis and skewness for first of the data and second of the data, and you compare. So, you can tell about whether you have statistical changes in the data set or not. So, how do we display these data set? What kind of the plot we can do? So, that can be done by box plots. Box plots gives you information about the probability distributions of the data set. So, that can give you the minimum value if you have minimum extremes or minima. So, that can be sometimes represented by outliers, a median value of a median value, and then maximum value, which is also sort of sometimes outliers, first quartile and third quartile. This is basically the information is conveyed by the box plot, and box plot is kind of a measures which basically kind of is beautifully explain the variability or the distribution of the data set when you comparing multiple parts of the data set or multiple stations of the data set or multiple regions of the data set, like that. And there is another type of the data is basically we can calculate histogram. Histogram is when we are dividing into data into frequency distribution or data distribution, and then you can give it whatever the size shape it is. It could be a sort of empirical distribution function, and that will tell you about what is the total shape of the distribution of the data set. It will also highlight the outliers, sometimes it will give you the skewness information, sometimes it will behave like a normal distribution, the bell curve, and sometimes it will also give you the idea about the distribution shape. Then there is another method is called time series data plotting. So, that will tell you about the trend in the data set, that will tell you about anomalies of the data set, where which year you have extreme rainfall event, where we have which year we have very high magnitude flood event. Is there any correlation with the flood and any given hydrometeorological conditions of that region, whether rainfall extremes and flood extremes are matching with together or not, for example. Then there is a seasonal pattern, whether the seasonality of the flood has also changed or it has remained the same. You can also calculate through the data set itself. So, therefore, you can basically use some sort of time series analysis which can give you the trend analysis, which will tell you about the data direction, which will analyze the long term progression of the data or long term trend in the data set, seasonality decomposition, which can break down into the components, which can basically tells about how the regular, how irregular or regular patterns it is there. Suppose when you are talking about the region where we have southwest monsoon are dominating monsoon season, for example, in that region we always see that floods are coming in more predominantly in June to August, September or October, or before October, So, that is the month where we have more occurrences of the flood, that is called which can tell you about the regular pattern or seasonality. It is also possible that floods are changing their behavior. Now, it is occurring more frequently in the early season of the monsoon rather than the previous historical data set. That can be also be done by using this kind of analysis. Then stationarity testing, whether your data set has been changed through the time or not. Is it stationary or non-stationary behavior? You can check the data set and using the stationarity testing also. Then you can also talk about the autocorrelation analysis. Autocorrelation is very simple. If you recall, we have talked about ARIMA model, auto-regressive moving average models, that is based on forecasting of the time series. So, autocorrelation analysis is basically we are looking back into the previous lagged time of the data, and we are trying to find out which lag time series of the data sets are highly correlated with your current step value. What is the importance of this? Basically, we can tell about, let us say we have found that consecutive past 3 days rainfall is basically dominating or influencing the floods behavior or like that. So, that is called sometimes the memory of the system, how far in the historical period it influenced the current event, like that. So, that is basically, and that is the same principle where we have developed multiple linear regressions or some sort of forward network deep learning models have been set up like LSTM and all. Then there is a probability distributions we have talked about. There are multiple probabilities. Let us say if you are not talking about only the extremes, if you are taking the whole data set, there are multiple distributions we can fit. For example, normal, log normal, gamma, Gumbel, GV are extreme extreme value distributions like that. So, what is the advantage of this probability distribution function? Basically, it gives you the probability information about your different values. Why it is important? Because once you have the probability values, you can convert back into the return magnitude, return period, and then you can calculate what is the value of, let us say, 100-year return period flood, something like that. So, that is basically can be used to modeling the method. For example, we can talk about which EVT or extreme value distributions are better for which type of events. We can do that some sort of impact assessment when we know that okay, these kind of the events are more frequent or frequency is higher, or let us say in the previous set of the data set and this set of the data set we have more frequent occurrence of certain magnitude events, then you can say that this is a more impact are posing to the public health or infrastructure design or water scarcity management, and then we can design accordingly like that. Then we can talk about return period of different magnitudes, whether crossing above 10,000 QMX or let us say 5,000 QMX, like that. These are the floods magnitude. Similarly, we can talk about what is the magnitude of rainfall which is crossing above, let us say 200 mm in one day or 100 mm one day, like that. So, that can be done by using fitting these kind of the extreme value distributions and can calculate what is the return period. And once we have the return period, once we have the magnitude, once we have already done the frequency analysis for impact assessment, we would be able to focus on the planning. Whether we need to do some sort of infrastructure upgradation or we need to install a completely new kind of structures because the older one is not no longer able to withstand with the changing conditions like that. So, in the EVT approach, we have already discussed in the previous classes that there are two methods which basically are very famous for calculating your extreme values from the time series, which should be independent. So, that is one is called block maxima. We divide the data into different blocks and then we calculate what is the maximum value. Usual practice is we can calculate take out 365 days which are year, and then you can calculate what is the maximum value of each year, that is called block maxima. Then there is another basically approach is peak over threshold, where you define a particular threshold and you say that okay, crossing above that particular threshold will be considered as a flood. So, it is possible that in one year you have multiple floods which are crossing above thresholds. It is also possible that in one year subsequent dates you have the floods which are crossing above that threshold, but that will not make sure you that whether these two events are independent or dependent. So, basically possibly when these events are occurring together at within 1 or 2 days lag period, it is higher chances that these events are dependent with each other. So, therefore, we have to, when we are applying the PQ or threshold, we have to take care of these kind of situations as well. What is the importance of return period in extreme event forecasting? Because when we have return period, it will tell you about 100-year flood, it will tell you about the infrastructure design, it will tell you about the disaster preparedness, it will tell you about the heat waves pattern or exposure or regional vulnerabilities like that. It will also tell you about urban planning. For example, if you are talking about heat waves, let us say you have different cities data set and you can calculate let us say how the heat waves have been evolved across different cities. So, you would be able to tell to the local government that okay, these are cities are located near to the Himalayan region. We need some sort of different types of urban planning compared to those cities which are near to the coastal region. So, because it might possible that the extreme weather events are slightly different or completely different from these different sets of the cities like that. So, therefore, once we have the return period estimate, once we have the magnitude estimate, once we have the nature of the climate extreme classification, you can basically tell about to the local government or the national government or the state level authorities how do we plan perfectly for that particular region urban planning. Then there is another so whatever we have discussed about, it is revolving around one kind of parameter, only one parameter, either it is rainfall extreme, either it is flood extreme, either it is drought extremes. We are only talking about only one parameter, one variable, right. So, basically it also might possible that when you are talking about floods or droughts or rainfall extremes, there are multiple variables are interacting with each other, and therefore, you have some sort of extreme events which are occurring. So, that is called multivariate analysis, where we are not focusing on only one type of variable, but there are sets of variables. It could be, let us say, rainfall, soil moisture, floods, or let us say some sort of vegetation cover, multiple factors together. And then you basically try to make a correlation out of it, and then you can tell that okay, which variable has significant role on promoting if the floods are crossing above certain thresholds. So, that kind of the analysis can be done and can tell you about the more detail about the governing mechanism of extreme flooding events like that. So, how do we do that? Basically, the correlation analysis can be done by two methods, that is Pearson and Spearman correlation. That is a correlation matrix. There are also instead of this, we can also do some sort of tau correlation, we can also do some sort of R square linear correlation. So, these are the linear relationship between continuous variable with a here we are assuming some sort of normal distribution assumption. But here when we are talking about Spearman, we are using some sort of monotonic relationship without assuming any kind of distribution. So, this is distribution free correlation method and suitable for ordinary data set like that. So, this basically method can tell you about how these two variables or 4 variables or n variables are correlated with each other. Then there is another analysis. Let us say you are targeting flood, okay, or rainfall extremes, and you have 100 variables that can influence the rainfall or flood extremes. How do we select which variable are the most important one? So, that is, or let us say, how do we select all of the variability within the data set in, let us say, can be explained by only 2 or 3 variables. So, that is the how we can do that. This is basically done by principal component analysis, where we basically simplify the large set of the data set, we reduce the dimensionality of the data, and that basically the reduced dimension of the data can be used to model the extreme events of a certain regions like that. So, that is the advantage when you are talking about multivariate. We can leverage the whole variability of the multivariate data, and we can reduce the number of variable, so that our model should not be too complex and we cannot explain the output and the input relationships like that. So, that is one way we can do that. There is another way is canonical correlation analysis, that is basically a sort of exploration relationship on variable set of analysis, and here we can also use some sort of maximum correlation canonical variables, and then we can do some sort of application in the climate research and agricultural studies like that. There is another multivariate approach which are very famous and now these days, that is called Kapula based method. copula is basically a kind of joining two probability distribution functions together is kind of the meaning of that. So, suppose we have 2 or 3 variables which are happening at the same time, and that is basically because of their interaction it might possible that climate extremes or extreme events can amplify. Then how do we define what is the relationship between these 2 or 3 variables like that? So, for this we can use some sort of copula method to first define the marginal distributions of the data set. Once we have the information about the marginal distributions, we can basically we can basically club it together and to form some sort of copula function, and that copula function can tell you about what is the relationship between a variable A and variable B, and that is basically influencing variable C like that. So, there is a multiple types of copula is possible. Bivariate, trivariate copula are very famous in the hydrological studies or climatic streams. That is basically can be done by multiple different types of copulas like Gumbel copula, or there are multiple copulas which can do that. So, this copula method or multivariates are very famous in when we are talking about compound extremes. Compound extremes, when two events are happening at same times, that basically amplify the effect of these extreme events, and therefore, that will basically enhance the risk of disaster planning like that. Copula can be also be used for relationship between multiple variables, which can be rainfall, river discharge, flood modeling. So, therefore, when we are talking about flood modeling, we have to know about how high rainfall and river discharge are related, because high rainfall often leads to floods, but not always in a linear or independent manner like that. Then apart from more advanced statistical analysis like copula and all, we have machine learning methods as well. So, that machine learning and AI techniques can also be used to do some sort of multivariate analysis, and that can give you information about how a target variable, let us say flood or drought or rainfall extremes or heat waves, are related to a set of variables, let us say 40, 50 or 30, 40 like variables like that. So, how do we do that? There are supervised method which is random forest. We can classify our climate extremes, we can predict climate extremes. There is a support vector machine, we can basically classify the weather patterns, we can identify the predictor of the climate extremes. Then there is a gradient boosting algorithm which are also there. Then there is a deep learning method which basically can be used to for example, CNN, cubic convolution neural network, and there is a LSTM, a long short term memory models, where we can use some sort of specific spatial data types, spatial features we can learn. We can manage high dimensional data set, we can do some sort of climate predictions, we can do some sort of maps environmental variables like that, and that can tell you about what is the applicability of the deep learning model in the climate extremes area. There is unsupervised learning which can be k-means or hierarchical clustering, which can basically cluster your data into different parts, and that can help you to identify the climate pattern classification, or where we have the similar weather events, or where we have the climate change analysis, which area is highly prone to climate change, climate extremes, and grouping the related climate events in one part. Let us say you have multiple climate events data set of a particular region, you can group it together. Okay, these areas are similar behaving, so therefore, we need some sort of similar management practices like that. Model evaluation and validation are the one of the critical step. We have discussed about this in the previous lectures very detailed manner. Model evaluation and the validations are done by statistical models. For example, we can do some sort of RMSE, MAE, R square, AIC, BIC criterion like that. There is a machine learning models where we can do some sort of accuracy, precision analysis, recall or F1 or like that. These kind of the indexes we can use to tell about what is the overall accuracy of the machine learning models. Then there is a cross validation methods. Let us say you have lesser number of data set, you can do some sort of k-fold cross validation algorithm. You can do some sort of leave one out cross validation algorithm that basically can manage your data and can tell you about how well your model is performing. So, this is the definition which we have written here. For example, root mean square error mean absolute error, the coefficient of determination, and the archaic information criteria and Bayesian information criteria is like that. So, therefore, we use these kind of the criterion or the metrics to understand how well our models are behaving. There are when we are talking about k-fold and leave one out validations, we have large data set, or we need to do some sort of thorough validations in the model. We can use these two types of methods like that. And the important steps is basically when we are preparing our data set for some sort of climate extremes modeling or statistical modeling or multivariate analysis, the very important step is data pre-processing and the cleaning, because if we have already pre-processed the data, which means we know that the data is error free, there is no gaps, and that has been done by some sort of interpolation or imputation techniques or some sort of gap filling techniques like that. Once it is done, a temporal aggregation, we can basically aggregate the data in daily and monthly and yearly or annual manner, and then we can analyze the pattern. For example, daily pattern, monthly pattern, seasonal analysis, or long term annual patterns, and then we can try to find out what is the overall behavior over the times like that. It is also possible, let us say, when you are talking about the data set which are coming from different source. So, for example, let us say you are talking about the data which you are taking from climate model. Okay. So, climate models might produce some sort of uncertainty or biases. Why? Because the climate models are developed, let us say, in a certain region, it is focusing on the Europe or America or some sort of region, or maybe it is possible that in the climate models we have some sort of processes which are not accurately representing the ground conditions. So, because of these inhomogeneities, we or in lack of the information, we may have the data which are produced by the climate models might have some sort of uncertainty with the ground observations. So, how do we correct these data? That can be done by bias correction techniques. What are the bias correction techniques? That can be done by quantile mapping or let us say delta techniques like that. That basically can adjust the error of your data, which is systematical error in the data set or the climate originated data with your observed data, and can reduce that error like that. There is some sort of statistical downscaling that is basically can be done by we have to large scale data set, and we have to do some sort of local analysis like that, or we have to make some sort of high resolution data set, that we have also do using the statistical analysis and like that. Then there is another step is basically visual analytics and GIS mapping, because once we have done everything, it is very important to know about how we can do the spatial distribution, how we can do some sort of regional analysis, how we can do the temperature anomalies, precipitation anomalies, or different types of if you need some sort of spatial interpolation so that we can have a better smooth data set like that. How do we do that, this analysis? We can do some sort of analysis in QGIS, ArcGIS, or some sort of Google Earth Engine or GIS softwares. Where is the application of these area? We can do some sort of flash flood area identification, urban heat island, or rainfall region, or one climate zones like that. How do we choose the right method? Basically, if you are talking about a spatial and temporal analysis, when we are talking about spatial analysis, geospatial analysis, spatial interpolation or visualization method, the spatial data, or when we are talking about the temporal analysis, we are primarily looking at the time series method, forecasting and extreme event evaluations like that. It is also we have to think about when we are talking about univariate and multivariate. Let us say you have multiple variables which are interacting with your extreme events, it is better to go with the multivariate, but we can start with the univariate technique so that we can have understanding about how our data is behaving. And so, overall in the climate data analysis process, we have to do some sort of exploratory analysis, descriptive cluster and correlation analysis, that will tell you about we can then move towards the predictive analysis, time series forecasting and supervised machine learning or unsupervised methods, and then we can think about some sort of statistical inferences, and then we can do some sort of uncertainty or analysis, or some sort of error analysis like that. That can tell about the whole modeling process of the data set. So, this is overall a broad overview of how we can do climate extreme analysis using whatever we have discussed in the previous classes. To summarize in one class, how we can do that, a range of statistical and machine learning models. So, in this lecture we have primarily talked about a range of statistical and AI tools that are essential for analyzing the climate extremes. We have also discussed about methods, how do we select these different types of methods, what should be our goal, and when we should use a particular type of the method like that, and how do we combine approaches to get a better insight about how we graphically enhance our capacity to understand overall pattern of the some sort of climate extremes like that. So, this is for the today's lecture. In the next lecture, we will talk about how we can do some sort of integrated case study project analyzing recent extreme events using whatever we have so far learned from the analyzing the analytical methods or some sort of statistical approaches, step by step procedure for different types of processes like that. Thank you so much for your attention.